You are welcome to the GMATS 41's YouTube channel. In this video, we are going to give attention to this topic in physics. Simple machine. Now this topic is going to be broken down into three parts, okay? In the first part, we are going to look at the basic key concepts in the study of machine. In the second part, we are going to give attention to types of machine and their velocity ratios. And of course, in the third part, we will look at further calculations in the concept of machine. Now, have you heard of the word machine before? If you have heard of that, what came to your mind? Alright, the machine in which we write, or the machines which are used to carry out tasks, jobs, works, alright, either at home or in the industries. In either case, anyway, in this class we are going to learn what simple machine is all about. To start with, we are going to do something first, okay? You watch me. I've got this paper, alright? I'm going to try to tear this paper. You watch and see what is going to happen. Let's see. I'm very strong, okay? I'm very strong, yeah? And now let's go. I want to tear it. I'm going to apply a lot of effort in order to see. Oh my gosh. This is tough. Well, I don't want to fracture my fascia bones. But you see that it's not easy. When I am done growing, I'll try to get it tall. Now you see, this is quite difficult, isn't it? Just to tear this, finding it very, very difficult. Good. I'm strong, you know. I'm strong, I told you, don't joke. Don't play this GMATS 41. But, oh my gosh, it was tough. The effort I applied was not funny. How about I do this instead? Okay, you know this scissors. Scissors are applying all this effort and you saw what was happening to my fascial bones. I would just turn old overnight. Just watch. Are you there? So how about I go this way, you know? And then we are going. That is interesting. I'm even smiling. That's good. I've cut this into two parts. So you see, I can still do same. We are going. As I'm cutting, I'm smiling, you know. Can see that? No much stress. So what's the idea here? In the first instance, I try to manually tear this, you know. I'm using my hands with my strength. Okay, so I can call that a manual process. Now in the second case, I decided to use a device. Okay, this is scissors. Alright, this is scissors. And then this device made it easier for me to cut this paper. Okay? The device made it what? Easier and even perhaps faster to cut this paper. So this device can be called something. We can call this device a machine. And of course, this is a simple machine. Alright? And with what you've seen demonstrated, we are going to define simple machine, okay? We're going to define simple machine. Are we ready? So a machine is defined as a device that makes work easier and faster. A device that makes work what? Easier and faster. That is simply what a machine is. Alright? Good. So you have the definition as shown, so you can copy it down into your notes. If you are in O level, okay, secondary school, you're preparing for JAM, you're preparing for WAEC, NECO, external GC. If you are an undergraduate in higher institution, say 100 level, 200 level, so you need this topic, right? You need this topic. And it's very interesting. You want to follow along. Knowing the concept of mechanics, you meet this topic, simple machine. So any device that makes work easier and faster is called a machine. Now, in the study of machine, there are key concepts that we usually encounter. In fact, we don't play with these concepts. because when it comes to the application of the idea of simple machine, we usually refer to these concepts. And so we are going to highlight these three concepts. We will define them and then look at their mathematical relationship. Is that okay? In the study of machine, we talk about things like the mechanical advantage, we talk about the velocity ratio, and of course we talk about the efficiency of the machine. But wait a minute. Why do we actually talk about mechanical advantage? Now, if you take your mind back to when I was trying to tear the paper with the GMAT 41 strength, okay? Yeah. It wasn't quite easy when trying to do that manually. It was difficult. It was difficult to overcome that task, to tear that paper. Even though I was applying, I must tell you the truth. You saw it on my face. Enormous effort. I was applying a large effort. Are you getting me right? But then it was difficult to get that paper torn. So the manual process was tough. But when I picked that scissors, which is a device that makes work easy as it is, because it's a simple machine, I could easily cut that paper. I could tear it apart. And in fact, when I was doing that, I was even smiling, right? It was quite easy. So it means that using a machine to do a particular work has an advantage over manually doing that work. This advantage that the machine has in overcoming a particular task, a load, is what we call what? Mechanical advantage. So we are going to define mechanical advantage. I'm going to use MA for it. MA, mechanical advantage. So we define mechanical advantage as the ability of a machine to overcome a large load through the use of small effort. Once again, the ability of a machine to do what? Overcome a large load by using a small effort. That is the advantage of a machine, called mechanical advantage. So this is the idea. You have a load you want to overcome. Alright? Now, you are using a small effort to overcome that load. Like you saw what happened with that scissors. I was just using a small effort, compared to when I was trying to use my hand to tear the paper. Now, by using that small effort on that device, that simple machine, which is the scissors, I was able to overcome a large load, a difficult task of cutting that paper. So that advantage is called mechanical advantage. Ability of overcoming, of a machine to overcome a large load using small effort. Now, from that definition, we can actually bring out a mathematical equation for mechanical advantage. Remember this. You, which maybe let's say the human, alright, or the operator of the machine, you will give in effort. You will work on the machine. You will apply a certain effort. Are you following, right? Force on the machine. Then the machine will bring out an output. The machine will bring out a result. And what is the result that the machine will bring out? The machine will convert the effort you gave to it to overcome that load for you. So look at the connection. The operator, largely I would say the human, works on the machine. Take note of that. The operator does what? Works on the machine, and then the machine works on the load. And what that machine does on the load is the output. Now, in the definition of mechanical advantage, mathematically, we can express it as load divided by effort. Remember the idea. The operator of the machine will put in effort into the machine. That will come as the denominator, input. Then the machine will convert the effort given to it to overcome the task, the load. That will be the numerator. Now we're going to take this as equation 1. And that is the mathematical equation for mechanical advantage of a machine. Now, you followed along when I talked about you put in an effort into the machine as the operator. Are you following, right? And then the machine will convert that effort to overcome a large load. What you put in is the input. What the machine does is the output. And the machine works on the load, which means that this formula can still be written as also mechanical advantage can be equal to the load is the output, what the machine does. So I'm going to write output And then that is going to be divided by what? Input, because the effort is the input. And so we can call this equation A because it's still the same as equation 1. What is the unit of load? What is the unit of effort? The unit of load is Newton because it's actually a force. Are you following, right? It's a weight. The unit of effort is also Newton because it's also a force. What you put it into the machine, you apply a force. Like when I was trying to cut that paper, I applied a force on that scissors, which is a simple machine there. And then the scissors, using the sharp ends, applied a force on that load to cut it. So load, effort, these guys are forces. Am I communicating? Therefore, they have the same units. Now, if they are forces, you want to take note, please, that mechanical advantage is also called force ratio. Since this guy is a force, this one is also what? A force. Mechanical advantage is called what? Force ratio. So you take note of that. And because mechanical advantage is force ratio, it simply means that it does not have unit. Take note of that. Mechanical advantage does not have unit because it's a Newton quantity divided by a Newton quantity. That mechanical advantage therefore becomes dimensionless. I hope I've communicated, right? If you have any question, feel free to use the comment section, drop a question, and I'll be right there to respond. However, don't forget you can become a member of this channel. Subscribe to this channel, then go ahead and support this channel in order for you to get maximum benefit again from this channel. Click on the join tab just below this lesson, alright? You see that? Join. Click on it. Then kindly select the GMAS 41's platinum or diamond level so as to be able to follow up with our lessons. Is that okay? Alright, we are going to give attention to another key concept when talking about simple machine. This time around, the velocity ratio of a machine. Velocity ratio. And sometimes somebody may just wonder, velocity ratio, why this idea of velocity ratio in the study of simple machine? Well, I was just thinking aloud and because I asked myself that question, when we talk about mechanical advantage, ratio of load to effort, it makes a kind of sense, the advantage of a machine. Velocity ratio, what's velocity doing here? And of course, I came up with an interpretation which makes good sense. And I'm going to tell you, you see, velocity we know in the concept of motion is distance over time. Distance over time. When you are making use of a machine, okay, like I have these scissors trying to cut, this paper, you notice that as the effort is being applied on this machine, alright, the effort is being applied with time. Am I communicating right? It's being applied with what? Time. And the effort covers a certain distance. The effort does what? Covers a certain distance. If I go this way, you notice as the effort is being applied on this device, it's cutting this paper. Are you following right? Now, the extent to which the distance goes will determine also the extent to which the task will be performed or the load will be pushed. Are you getting the point? These things happen with time. And the truth is the time during which you're working on the machine is the time during which the machine will also work on the load. Which means that the time in the case of the effort and the time in the case of the machine working on the load, they'll be the same. They'll be what? The same. Now, if velocity is distance over time, it therefore means that the idea of velocity ratio, all we have to do is to take the ratio of the velocity in terms of the effort and the velocity in terms of the load. Remember, you must apply effort first before the load will be overcome by the machine. So, this is really what brought in the idea of velocity ratio to the study of simple machine. And of course, I'm going to write here velocity ratio as the next thing we want to deal with. Okay, velocity by the effort divided by velocity by the what? Load. And like I said, velocity is distance over time. So this velocity of the effort will now be distance moved by effort. Permit me to use small letter e for that. So distance moved by effort, small letter e, divided by the time during which the effort acts. Then that is going to be divided by Distance moved by load, permit me to use small l, and that's going to be divided by the time during which the machine acted on that load. And the time in both cases will be the same, like I explained already, which means that these two times will be the same, they go off, and I can conclude therefore that my velocity ratio, VR, will be equal to distance moved by effort, E, small e, divided by distance moved by what? The load, which is small l. We are going to take this as equation 2, the second key concept in the study of simple machine. Please take note that small e there represents what? Distance moved by effort. And small l represents what? Distance moved by load. So simply, velocity ratio is the ratio of the distance moved by the effort to the distance moved by the what? Load. I just use this to explain the reason why we call this velocity ratio. You know what brought in velocity in the first place here? But this is the general formula when talking about the velocity ratio of machines generally. Is that okay? Velocity ratio of machines generally. If you now start talking about different types of machine, each machine has its own velocity ratio formula. But plus minus, whatever the formula of the velocity ratio of a particular machine is, all of them is obtained from this general formula, which is distance moved by effort divided by distance moved by load. This is cool, right? Now we want to find out the factor that affects velocity ratio and what velocity ratio does not depend on. Please you watch the screen as this appears, okay? Factor upon which velocity ratio depends. Alright? Velocity ratio depends on the geometry, that is the shape of the machine. Velocity ratio depends on what? The shape of the machine, the geometry of the machine. And that is why I told you that different machines have different velocity ratio formula, although all of them are obtained from this distance moved by effort divided by distance moved by load. But now, depending on the shape of that machine, you can now get a special formula for the distance moved by effort. You can also get a special formula for the distance moved by load. So take notes, the geometry of a machine affects velocity ratio. However, velocity ratio does not depend on friction. Velocity ratio does not depend on friction. You can put these two important points down in your notes as they show on the screen. Alright, we have explained the concept of velocity ratio. We're now moving on to the last important point or terms when studying simple machine. And here we are going to talk about efficiency. We're going to talk about efficiency. Efficiency of a machine. I am going to use EFF for it, okay? We're going to use EFF for it. And quickly, without wasting time, we're going to define the efficiency of a machine. Follow through. Efficiency of a machine is defined as the ratio of useful work done by the machine, which of course is the output work, to the useful work done on the machine. Take note. You know the work done by the machine is the output. Output, work done by machine. The useful work done on a machine is the input. The useful work done by the machine is the output work. So the ratio of the useful work done by the machine to the useful work done on the machine expressed as a percentage is what we call the efficiency of the machine. In fact, when you talk about efficiency of anything generally, you are trying to kind of quantify the let's say the potential, okay, how well that thing can perform. Now from that definition, we can actually write the formula of efficiency to be equal to useful work done by the machine divided by useful work done on the machine. We're going to take this as equation 3, okay, equation 3. Then we can still work on this efficiency formula. The useful work done by the machine, like I said, is the output, where the load comes in, because the machine works on the load. Whereas the useful work done on the machine is the work input, and that is where the operator, the human that is working on that machine, the work that person is doing on the machine comes in. Like when I used these scissors, the effort I'm applying, I'm working on this machine, then allowing the machine to do work on the load. So the useful work done on the machine comes from the person operating the machine, and that is the input. So I can write this formula as work output divided by work input. I'll call this equation 3a. And then quickly, let us do something. We know the basic definition of work done. Work done is equal to force times distance. Work done is equal to force times distance. So we can actually break down this formula in this work, work output, work input. We can substitute force and distance, that is force times distance, for them, so that we can see what this formula will look like. However, I would like you to put down this quickly. Dimensionally, and that's why in terms of units, work and energy, they are the same. Simply energy output divided by energy input. And remember, when you are studying the concept of energy, depending on the field in which the energy comes in, you can have something like mgh. Are you following, right? You can have something like half mv square. You can have something like power times time. All these things are also energy formula. An examiner can test you in those areas as well. So you take note of that. All right. Having said this, I'd like us now to move on, break down this work into force times distance. So this efficiency formula is going to still be written as, take a look at this, work output. That comes in terms of what the machine is doing. And we stated from mechanical advantage that the machine works on the load. So if we have work output work, it means that it is going to come from the concept of load. So force times distance there will now be the load itself, which I am going to use capital L for. I'm going to use capital L, and then effort, I'll use capital E. Okay, so in terms of work output, this is going to be the force by the load, which I'm going to just use the load because this load is already force, times the distance moved by the what? Load. Because we said our force times distance is work. So coming here, this is going to be load times distance moved by load, which is small l. That's going to be divided by, place all these things are expressed in percentage, so it's times 100, times 100, take note. So load times distance moved by load, then all over work input comes in terms of effort, what you are giving to the machine, all right, the person operating it. So the effort of that person, and you know that this effort is force also. So the denominator work input is going to be effort times distance moved by effort. Effort times distance moved by effort, and then we're going to multiply this by 100. So looking at this, take note of something very important. This load over effort is mechanical advantage. Let me indicate. Load divided by effort is equal to mechanical advantage. So in place of this L over E, we can fix mechanical advantage. Then take note that the distance moved by load divided by distance moved by effort, it looks like velocity ratio. But the difference is that in velocity ratio formula, it is distance moved by effort over distance moved by load. This one is distance moved by load over distance moved by effort. So if you compare this guy with this guy, it's as if the velocity ratio was turned upside down. Remember, this velocity ratio is over 1. So for this L to go up and E coming down, the distances, according to what you're seeing here, it means that 1 will go up and velocity ratio will come down. So distance moved by load over distance moved by effort is simply 1 divided by velocity ratio. And so the implication will now be that efficiency formula of the machine can still be written as load over effort, I'll fix mechanical advantage there, then times distance moved by load divided by distance moved by effort is 1 over velocity ratio. 1 divided by what? Velocity ratio. Then multiply by 100 once again. So we can conclude therefore that efficiency can take this formula again. Efficiency of a machine is equal to mechanical advantage times 1, which is the same as mechanical advantage, We are dividing it by velocity ratio, because this is over velocity ratio. Then multiply by 100. And this is the basic formula, all right, for efficiency of the machine. Usually when you see it, it is expressed in this form. But take note that all these equations, they are the same thing. They are the same, this, and this. Let's call this equation 3a prime. Equation 3a prime. Or let me just call it 3b. Okay, then this 3c, asterisk, asterisk. I decided to highlight this particular one because most times the efficiency formula is written in terms of mechanical advantage divided by velocity ratio then times 100. But it's the same as all these ones. You see, we derived it from this guy. Alright, this is great, and I hope you enjoyed this analysis. Please, I want you to take note of something. I want to put it down. It's going to appear on the screen as well too. For a perfect machine, for an ideal machine, that is one in which there is no loss. Everything is occurring perfectly there, even though we don't have such machine anyway. But I want to take note of that, and examiner can ask a question on it. For a perfect machine, for an ideal machine, mechanical advantage is equal to velocity ratio. Mechanical advantage is equal to velocity ratio. Therefore, efficiency of a perfect or an ideal machine is equal to 100%. If mechanical advantage and velocity ratio, they are the same thing. It's just as if mechanical advantage is 5, velocity ratio will also be 5. When you divide, it will give you 1. 1 times 100 will give you 100%. So in terms of percentage, efficiency of a perfect machine, of an ideal machine, is 100%. I know that 100% in decimal is equal to what? 1. So these are the 3 basic concepts, terminologies that we encounter when we are studying simple machine. Are you following, right? You've seen their formulas, don't play with them. Is that okay? In part 2, where we are going to look at types of machine now, we will now see the specific velocity ratio formula for a given type of machine. That's going to be in part 2. Like I told you, in part 3, we'll see further calculations. In this part 1, having defined these key concepts, we're just going to pick 1-2 questions, solve, and see how we apply what we've established on the board. But before we pick any question, please take note of what I'm about to say here. This formula for efficiency is where you multiply by 100. You use it if you are looking for efficiency, if you are calculating efficiency. Does that make sense? Now, what if in the question efficiency has been given to you? Let me assume you are now looking for any other thing but not efficiency. The value of efficiency has been given. In that case, you will no longer multiply by 100. This 100 will come as the denominator of that efficiency. So the formula will look like this. You can copy it into your notes. This is when efficiency value has been given to you in the question. The formula is going to be efficiency over 100 equal to mechanical advantage over velocity ratio. You don't need to multiply by 100 again, because mathematically this 100 will come below here. It's like you're dividing both sides by 100, okay? So you take note of that in case you're solving any question and efficiency value has been given to you. Use this. You only multiply by 100 if what you are looking for is the efficiency. To learn how to make use of this formula in solving questions, click on this and you will see questions being solved using what we've learned so far. I'll be seeing you in part 2 in my next video. Take care of yourself and remember to take your studies seriously.